All right, it's 11 o'clock. I think we'll start. So, yeah. Stephen, is it good?
Sorry, I was on mute. Yep, let's get rolling now. So it's 11 o'clock.
All right, so I will go ahead.
No, I was just going to say I'll let you guys introduce yourselves. I was stoked to have you back. As I mentioned, I was excited by your talk at the jam session, and excited to dig deeper into these topics. So thank you for coming.
Yes, and so are we. Thank you so much for having us. Soumitri and I are super excited to talk through this, and I am very excited to hear your thoughts and hear the questions. We will have 10 minutes after this presentation for questions. Obviously, if you have explanation that needed to be expanded, do ask. But for discussion questions, I would love it if we can hold until Soumitri finish the presentation. It's jam-packed, so there's a lot to learn and a lot to talk about afterwards. So introduce, my name is Tina Nguyen. I am the Enterprise AI and Machine Learning Portfolio Manager for US Bank. So I curate a portfolio of use cases using AI machine learning solutions for the enterprise. So the part of my job that is extremely rewarding and exciting is I get to work not only with executives on use cases for real life business problems that we can solve, but also I get to learn and work with the top AI machine learning practitioners. One of them is here with us today. So that's Soumitri, our leader of our AI team. So I'm going to pass on to Soumitri to start introduce himself and begin our session.
Yeah, thanks, Tina. Again, I am AI leader at the US Bank. I just want to, before I jump in and go through some of the topics for today, I just want to mention that this is a very sensitive topic, and for reasons that may be very obvious for everybody on the call, I just want to, come up and show you the disclaimer that most of the views, almost all of the views that are in this presentation are my own and Tina's, and not that of our employer, either current employer or previous employers. But speaking of current and previous employers, I just want to give you a brief overview of my career. So I started at Honeywell as a research scientist and kind of grew along. And up until last year, I was a senior fellow, and I was leading the fellows program at Honeywell. And most of my experience have been in smart home with the smart assistants that have proliferated now, but we were doing some of that stuff even before these, and we'll talk about some of those in a minute. Industrial IoT control systems and things like that. And then recently, about exactly a year ago, I started at US Bank as their AI leader. Couple of things on that. We have a bunch of use cases in analytics, in video analytics, in extraction from document, in fraud detection and things like that. One of the interesting things about the financial industry is that it's a very regulated industry, which means that we have an abundance of data, and digitalization is in full swing. It's at an inflection point. So it's been a great accelerator for AI and ML adoption. Coming to fairness and privacy, there are a bunch of checks and balances that are in the financial industry. And that's because it's been regulated, it deals with money, there are a lot of sensitive things. And so there are a huge number of checks and balances. And so it is probably one of the best industries to look at fairness, bias, and things like that in AI. I've been very fortunate enough to, and our group has been very fortunate enough in looking not just in fairness and bias in AI algorithms, but looking at it from the flip side, which is how can AI help in providing fairness and privacy and eliminating bias in processes and things like that. So it's been a very rewarding last year, and hope that it will continue to be that way. Coming to the topic at hand, which is fairness and bias in AI. I just want to start off with a simple example of something that I had done when we were at Honeywell. So we were one of the first company to come out with what people now term as a voice assistant. And so we came up with a thermostat that you can talk to. So you can say it has voice control, it has the same kind of triggers like you see things now, like Alexa or Siri or something. Our trigger was hello thermostat, and then you could say, program the thermostat, you could change the settings, you could ask for the weather inside, the temperature inside, the weather outside, and things like that. So that was a very rewarding, very interesting thermostat, a very interesting technical challenge for me. And still today, it's a very, I'm very proud of the work that we have done. And this was in 2012, so it used hidden Markov models. It didn't have deep learning models or anything like that. But the next more important market for thermostats for Honeywell was UK. And so the company decided we should also do this for UK. And so we said, okay, let's go to UK. And if we had just taken the thermostat as it currently stood and had released it in the UK market for speech recognition, this is what would have happened.
What's the buttons? No, they install voice recognition technology and stuff there. Voice recognition technology in a lift in Scotland. You ever tried voice recognition technology? No, they don't do Scottish accents. 11.
Could you please repeat that?
11. 11. 11. 11.
Could you please repeat that?
11. Whose idea was this? You need to try an American accent. 11. 11. That sounds Irish. No, American. Doesn't it? 11. Where in America is that? Dublin.
I'm sorry. Could you please repeat that?
Try an English accent. 11. 11. You for the same part of England as Dick Van Dyke. What's he using? Smarts.
Please speak slowly and clearly.
Smart ass. 11.
I'm sorry. Could you please repeat that?
11. If you don't understand the lingo, away back home to your own country. Ooh, is that talk now, is it? Away back to your own country? Oh, don't start, Mr. Bleeding Heart. How can you be racist to a lift?
Please
this
speak
goes
slowly
on
and clearly.
for about 3 minutes. It's a very funny video. So after watching the video, what would be the answer to these questions? Is speech recognition biased against Scottish people? And is speech recognition the one that is biased, or hidden Markov models, or deep learning models for that matter, if that would, those models that were used for this, are they biased against Scottish accents? And then finally, very interesting, thought-provoking question, am I biased against Scottish people for picking this example? These are the kind of questions that people are asking, not for speech recognition, but for many AI problems that we are all looking at right now. And I can assure you, at least for that, the answer to the third question is no, absolutely no. I'm not at all biased. And for the top two questions, I can tell you the answer is no. It's not biased, but we don't have an existential proof. And so the question is a little bit more deeper if we go into AI models in general. And the question is, are the models and the techniques, basically the optimization techniques, the architectures, the nonlinearities that we used in AI, are those that are inherently biased against a set of people or a set of training examples, or is it the underlying data that is being used to train them that is biased? The answer to this question is not 100% clear yet. A lot of people basically believe that it is the underlying data that is causing the bias. However, there is, again, no existential proof that just the models themselves can't be biased at all. But most of the blame goes to the models. Most of the blame goes to the techniques. People say facial recognition is biased. They never usually say that the underlying data, which is labeled faces in the wild, that was used to do this facial recognition algorithm is biased. So that's one from a practitioner's perspective. We need to look at and say and distinguish between what causes bias. Is it, again, the data that you're looking at, or is it the technique? And for the most part, it's almost always the underlying data. But we'll look at a couple of examples where maybe the techniques themselves need a little bit of tuning. So here is an outline of what I want to talk about. These are all things that came out when we had our jam session. And so I want to touch on all four aspects here. And I have a few examples on how these things have evolved over time. The main important thing is that at this point, at least, the explainability of these models is playing a huge role in either dispelling the bias or at least minimizing it. And so we should look a little bit more closer into explainability when we are developing models as practitioners. So we'll start off with looking at the types of biases that are usually found in machine learning and AI. But as we talk more about AI, there is a new technique that, and if you're a practitioner of AI, you know this technique very well. But if it is new to you, then this technique is called transfer learning. And there is some real good things that came out of transfer learning. And there is also a lot of things that may go wrong in transfer learning. And so you need to be careful about it. Now, transfer learning gives you these AI models that can do a lot of things, but for the most part, in most practical purposes, people are at the moment using it for what are called discriminative models, which is basically models that analyze an input and provide either a classification or a regression on the input. There are other set of models called generative models, and those models are the kind of models that are like deepfakes, for example, where they actually generate text or data. And those are things that have, at least at the moment in financial industry and in many other industries, have not taken hold as the main models that are being used. But they are coming, that it is coming. And so you have to be a little bit more careful with generative models. And so we'll look at a few generative models. They are both appalling and amazing. And so I'll give you a couple of examples of those. In general, and I'll not go too detailed into this one, there are a few set of known types of biases in machine learning. And these have been extensively studied. And when people studied these biases, they basically had an underlying assumption that if you take care of most of these biases in the data that you are using for training your models, for building your models, and in the data that you're using for validating and testing your models, then the amount of bias that is present in your models is minimized. So examples of these kinds of biases are samples, where you say, okay, make sure that the model you're building is built on a sample, but that sample accurately represents the whole environment. Exclusion bias is basically excluding a few set of features because there is thinking that they're not relevant for your model. Observer bias is like basically saying accepting the tendency of what we expect to see or what we want to see. Example of this is that if you see that a model is predicting that a nurse is always a female and you don't catch it, that's an observer bias, because for us, for a lot of us, that's what we expect to see for a nurse. Recall bias is basically, if you have labelers or people who generate the training data and they are of diverse mindsets, and there is an inconsistency in the bias or inconsistency and bias in the way things are labeled. And we'll see examples of that as well. And then there is finally the measurement bias, where the data that you want to collect is collected using a different measurement technique, and that introduces bias. The point I'm trying to make here is that if you take care of this up until like about 2018, I guess, if you took care of these biases and you made sure that the data that you're using to build your model is rid of these kinds of biases, these kind of known biases, you were pretty good. You could assure somebody that, hey, look, I did all these careful studies and then I came up with this model. And so, I think I minimized all kinds of biases that could happen in the model. However, that has changed for AI. And because the AI models have started increasing in their size quite a bit. And if you're using deep learning models or deep neural network models, it's almost impossible to generate the amount of data that you require to train it from scratch. And so what people actually do is they use a technique called transfer learning. And transfer learning is basically a simple technique where you take a model that is trained on a huge swath, a big set of data, and then you transfer the learning in that data to data of your own. So you start with pre-trained models, and then you train models of your own. So we'll go through examples of both images and text where transfer learning is used. And about 95% of every practical application that you see for either vision or for text is in AI models is based on pre-trained models and transfer learning. And it's very rarely used, the models are built from scratch. So what do they use for these pre-trained models? For text, these pre-trained models come from open text resources like Wikipedia, the Common Crawl, basically the whole web, books and things like that. And for images, all these pre-trained models come from a huge database of images called Imagenet. And about every backbone that, a backbone is an AI network that is used for transfer learning. And that network has always been trained on Imagenet. And Imagenet has been actually very, very useful in progressing the field of deep learning to where it is now. I mean, Imagenet came into being in 2011, 2012, and within a decade, the whole computer vision area completely changed. And the types of accuracies that you get for classification and regression and things like that are huge. So how is it done in images? So you take this Imagenet, which is like about 22 million images, and they're all labeled, and you take that and you take a random network and you train it, and this training is done by a few big companies like Google and Facebook and other companies like Baidu or Tencent and others, and they publish this base neural network or pre-trained model. Now, if you want to use you train a neural network model on your data to basically, if we are trying to figure out if what is the kind of data that is being presented for, is it ATM of one kind or another or something like that, then you use fine-tuning for training your own neural network. And this is how everything today is being used. None of the networks start with some data of their own and then try to train the final network. It always is based on a pre-trained network that uses pre-trained set of data. So now here comes the bias. Here comes the problem with the bias, is because how can you guarantee that this data is not biased? You can guarantee this because this is your data, and you can look at your data, you can do all kinds of tests on your data and things like that, but this you cannot. And so let's look at, and because this one is the basis for a lot of networks, let's look at how Imagenet was constructed. Imagenet was constructed in two steps, right? Collecting the candidate images via the internet, the Flickr images, and then there was a bunch of other image sources that they took. They took those images and then clean up the candidate image by humans, and then annotate those images by humans. So I mentioned 22 million images. So how did they do annotation for 22 million images? And so before we go in there, these are the kinds of things that are in Imagenet. There are these big synsets, as they call them. There's subtrees of like mammals and persons and things like that. And within those subtrees, there are another set of subtrees that are of humankind, kitty cat, different types of cats and things like this. And so if you ever wonder why do AI algorithms usually give examples in cats, this should answer the question. There's so many, 69,000 cat images in Imagenet, and that's the reason why you see so much examples in cats. So this is the data that was used, and the way this was done was using Amazon Mechanical Turk. And so people were paid money to look at a picture and annotate the picture, tell what's in the picture, and type it down, and then basically that was used to build all the models that we are seeing for vision today. So they also published the demographics of the people who did this. And so you will see the variation in the number of people, what is their education level, which country they belong to, what's their gender. The gender bias here is very interesting between India and the United States, and then their household status and things like that. So the social tendencies, the social biases that are in people's minds when they look at a picture just got transferred into this Imagenet when they annotated these pictures. And people don't realize that. I didn't realize this is what happened, how Imagenet was constructed. until I started digging in deeper. And so that's what causes the bias. That brings in a set of bias into your model, and you have no control over it because you really don't have the resources to come up with 22 million images of ATMs. And you have to use something like this, but this may actually have some bias. And so you have to be very careful when you're using this. So one example of the Imagenet, and this is a specific call out for a specific labeling. So there is a label for failure, loser, non-starter, unsuccessful person. And this was actually labeled. And there are some more, a little bit even more offensive examples that you can see. And this was kind of only pointed out last year or in 2019, late 2019, early 2020, and it was taken out of Imagenet. But up until then, these kinds of annotations already existed in Imagenet. So that's the kind of data that we are dealing with. And we all saw the facial recognition backlash that many of these companies took last year and stopped using facial recognition. So why did that happen? And that happened because most of the facial recognition models used two databases, Cassia WebFace and LFW, which stands for Label Faces in the Wild. The problem with these databases is that this is the racial distribution. The racial distribution for this, the most popular of them, it's 70% Caucasian. So now, do you blame facial recognition algorithms, which are here? These are the set of algorithms. You read through these algorithms, and if you're a geek, you will really, really get your juices flowing when you look at the kind of algorithms that are being presented here. But are these biased, or is this the one that is biased? And that is something that we're still grappling with at this moment. And for the most part, this paper, the paper that I'm showing here, is actually an interesting paper that came out, and it's called Racial Faces in the Wild. It's basically a play on labeled faces in the wild, and they have equal distribution. So again, be very careful when you're trying to do your models and you're depending on the data that those models use. So we'll move a little bit quickly now to text, and this is exactly the same thing that happens in text. Text is no different, but this happened in 2019. Up until 2019, you didn't have the Imagenet type of data for text, and so people were trying to train from scratch. But then this model called BERT emerged, and the emergence of BERT was actually named as the Imagenet moment for text, which means that this model could also be used for transfer learning. Basically, you take the model that is developed by Google or Facebook or OpenAI that is of this one. BERT is something developed by Google. Roberta is based something developed by Facebook. GPT-2, GPT-3 are things developed by OpenAI. And then you do the same thing as I showed before. You retrain your model for your specific document or whatever you do. There are two ways to do that. This is one way where you retrain this model. The other way is basically you take the model as is and then add something to it and start retraining it. Either which way, right, you're still doing transfer learning. So again, question really is, what is it that is being used by these guys to pre-train it? And the answer is Wikipedia, Common Crawl, Twitter feeds, and things like that. And so the question is, are those biased or are they not biased? Is the data in those biased or not biased? That's a very hard question to answer. I think they are biased, but they are biased because of the representation. It is the sample bias. So people may have heard of the the recent dismissal of a researcher from Google. This is a screenshot from the paper that Google didn't want their name on. And what this paper is saying, and this is called On the Dangers of Stochastic Parrots. What this paper is showing is basically the overview of language models that are pre-trained, right? And they are growing in size like crazy. And when they grow in size like crazy, so GPT-3 is the one that is out now. These two are not completely out yet. And you can actually, I am one of the favorite, fortunate guys who has an API for GPT-3. But look at the size and the data set that are being used for this. And so as these models are increasing, they are getting to a point where they are eliminating the need for transfer learning. And so what do they mean by eliminating the need for transfer learning? They have become so good at pattern recognition that you don't need to train the model to recognize a pattern. You can just give 3 or 4 examples. And so if you give one example, it's called one shot. And if you give a few examples, it's called a few shot. And the model is able to learn this and learn the language and start basically doing some fantabulous tasks like coming up with a paragraph or writing an essay on its own and things like that. And so you're not even able to do transfer learning with your own data anymore. You can just give some examples and the model is able to come out with outputs. So I'll give a little bit of pause here, and maybe we should just look at the first paragraph of this. So this is a paragraph or an essay written by this model called GPT-3. It is not written by a human. It is written by GPT-3. And it is the only prompt that was given was the prompt on social distancing. And so social distancing became a great, a big phrase for us over the last two years or, 1 year. And if you read this, it basically says, okay, there is a contagious disease and they must avoid meeting each other on streets. And so it shows or it portrays a very negative sentiment towards social distancing. Is this biased against social distancing or not? I don't know. I can't make that. But to me, first of all, this is amazing that this language model is able to come up with this nice essay on social distancing. So, but the most important thing and the really interesting thing about this paragraph is that this paragraph or this essay was generated by GPT-3, whose training stopped in October of 2019. So 2 months before the first COVID case was detected, training stopped. So it did not have any context of COVID. It did not have any context of social distancing, and it portrayed this image. So this brings out another point, is that these kinds of models, these language models and voice models and text models, we have to be careful because the social norms and the social expectations and social bias representations are changing constantly. And so when we are looking at bias in our AI models, it's not just enough if we ensure ourselves that the model has been trained with all kinds of data. We have to keep the model updated over how things change with time. That's another important thing to take into account. Here is an example again from GPT-3 as well. And so this is the generative model. The previous case was also a case of a generative model. This is another generative model experience, again using GPT-3. And so the prompt here was two blank walked into a bar. And so they say two atheists walked into a bar, 2 Jews walked into a bar, Christians walked into a bar, or Muslims walked into a bar. And then they counted the number of times there was a violent sample that came out because of this generative model. And it turns out that these generative models are biased against a specific set. And in saying that, I actually said the model is biased. And I should probably have said the data that was used was biased, but I did say that the model was biased. So these are things that we are grappling with at the moment. So there are multiple such examples that you can look out in the internet and find out. But let's now look a little bit into what can we do to alleviate these problems. So I talked a little bit about explainability. This is a pretty geeky slide, and so I don't want to go too much detail into this slide. But this shows an interesting way of testing your models. And what it does is, if you can look at this gray square here in all of these examples, there is a gray square. And what they do is they use the model and then they put this gray square by masking out parts of this picture and say, what is it that the model is predicting if this gray square keeps moving? And so I just want you to focus on this, the fourth column. And this is basically saying the classifier probability of the correct class, which is that as long as the square is not focused or not put on the face of this Pomeranian, the correct class is coming out as a Pomeranian. If this square is on the face of the Pomeranian, the class that is coming out is that of a tennis ball, which is what this Pomeranian is holding. This is a very good example of trying to explain what your model is predicting and why it is predicting the way it is predicting. And so this is again the same thing. This is a car wheel, and you'll see this part of the picture is what is causing it to do to say it is a car. And then this is a negative example where the Afghan hound, and this is what the model is. This is what the model is focusing on in trying to figure out if it is an Afghan hound or not. Again, interesting insights into what your model is doing and a way to explain why your model is predicting whatever it is predicting. Something very similar, but a negative example, is that of a husky and a wolf. So this is a very famous example. You may have seen this already. So in the Imagenet, there are a lot of examples of wolf. And almost all of the examples of wolf have snow in the background. And when they did the same kind of probing, they figured that, hey, this is a husky, but it's classified as a wolf. And why did it classify this as a wolf? Incorrectly classify this as a wolf. It's because there is snow in the background. And so if you do these kinds of probes, you know what your model is looking at and what kind of bias this model has. And again, explainability is key for these kinds of things. I will not go too much into detail about text, but you can do the same thing with text. There are a lot of probes that you can do with text, and some interesting things within BERT that actually tell you, the noun modifiers or prepositions and how prepositions are attended to, or co-reference and mentions are attended to, and things like that. These kinds of analysis can be done on text as well. And so I just want to end with this, some thoughts on mitigating the bias from a practitioner's perspective again. You have to be very careful and make sure that your population is represented when you're trying to train your data. Whenever possible, use transfer learning and open source on your open source model with representative data. Do not just rely on open source models. because if you don't have your own data and you can't do your own testing, validation, and things like that, you may run into problems. Use probes as much as possible. Use explainability tools. There is a nice tool called Lime. The Lime tool was the one that I was showing for the Husky versus Wolf. They give very good insights into the model and their prediction pathways, and so you should always look into that and make sure that you do a bias research and make sure that your model is predicting things the correct way that it should predict. Human biases and prejudices will creep into your testing and training data, so you have to be on the lookout for it. Sometimes the impact of these prejudices may be minimal, and that's fine. If the impact is pretty high, then it may be detrimental to your model, your project, and your company maybe. At least in the financial industry, there are very strict checks and balances, and there is always a model risk management and model risk aversion group and things like that. And so be careful about how you do your testing and training. And finally, I think we already mentioned about validation verification, but you should be very cautious about generative models. Generative models that actually bring out generative texts or bring out images of their own, or do image captioning. You give an image and try to come up with a caption for the image. Those kinds of generative models are based on inherent biases that are already present in the underlying data that has been used to do this transfer learning. And so if you are looking at those type of models, large AI models, then be careful in doing your due diligence when you come out with those models. So I'll stop there. I don't know if I went over, but if there are any questions, Tina or I can answer.
Yeah, we can just open it up to the floor here too, if you want to unmute yourself. I noticed there was one from Chris. Chris did ask a question. We can go ahead and get started with that. Can stratified sampling be used to even out the training data? And I'm not quite sure what he means by stratified sampling, but if he could clarify, or maybe you have an idea on what that is.
Yeah. So no, I don't. I can guess, but maybe he can talk a little bit.
Oh yeah. Hi. How you doing? Yeah. So I think that you covered it because I asked that question a while back, but I think you covered it in the section where there were data sets that came out with more evenly represented pieces of data. But I was actually wondering, do you know of any techniques to statistically detect the bias in the models? So it's kind of a hard thing, because unless you know what the bias is, it's almost like you have to have a system, maybe a adversarial system to verify whether or not the bias exists in the model in the first place.
Yeah, so very good question. I think we actually grappled on this even in the jam session. So if you know what you are going to be testing for, what kind of biases you are going to be testing for, this is probably a solved problem. You can test for it.
Mm-hmm.
However, I think the bigger problem is for the unknown unknowns.
Yeah.
And are there any unknown unknowns? And that is going to be a tough one. So one example for the known knowns are known unknowns are, maybe you look at the imbalance for the class on a racial or some other kind of bias axis. Even though you're trying to just detect faces, and if you want to test it on a racial bias, you can see, okay, my class is very much imbalanced in the input, right? But and that'll help you with with stratified data sets. But for the unknown unknowns, for them, that's yeah, I don't think we have a way at least at this moment.
And then I guess I have one more follow-up. So in the past, I had written a paper on computer vision. This was kind of before TensorFlow had come out. But you know, one thing that I did to generate my test set was you know, using 3D models and pictures of different backgrounds to kind of remove the bias for the background. Has there been much thought about kind of artificially generating these images and then, you know, in order to manufacture a, you know, quote unquote unbiased data set?
Yeah, there has always, you know, in the last 3-4 years, there have been a lot of, these are called semi-supervised methods, where you take your supervised image and then you apply a lot of transformations on those images. And so PyTorch or TensorFlow actually has a huge class of these affine transformations, as they call it. And they do stretching, they do flipping, they do color jitter, they do background jitter, and things like that. And so those are already being introduced into the model. So I didn't mention it for Imagenet, but all Imagenet images, when they are used in training models, they go through these affine transforms, where the background is removed and things like that. But when it actually comes to the detection mechanism, the whole detection mechanism is stays as is. So that's the reason why the snow background, you cannot remove this, just the snow background, because, you know, to manually remove a snow background requires you to use a AI method as well. I mean, not manual, but to remove the snow background requires you an AI method, and that itself may be biased. So.
Okay, thank you.
So any other questions? I think we have time for a couple more. We're, you know, we've kind of run over our time a little bit, but we're backing up against lunch. So if there's any kind of questions, I think there was, we can probably field a couple more. Any other questions for Soumitri?
I have a question. So thank you for your presentation, and as well as Tina. I was wondering, moving forward, as you mentioned with the unknowns, how do those things impact the situations where things that are affecting the overall data, your overall project? How does that affect it? Is it a point where these unknowns are revealed at some point, and then it was something that you were not testing for, but reveal itself? And how is the correction then embedded into the next phase of the data training and things like that?
Soumitri, do you want to go first and talk about that, and I'll cover?
You can go first, or I can go first, whichever way. I think you had a very good example of how you know, you were looking at inherent bias that was not initially you know, deciphered, right, in the jam sessions. You should provide that example, I think.
Yeah. So, you know, I think on the first couple slides, Soumitri mentioned besides the learning data and the techniques, there's also the systematic, where the system itself was built to optimize, right, to industrialize and make things smooth. However, with that, bias can creep in with us not knowing that. So the model could produce a very unbiased result, but as it's moved through the production stage until commercializations, when we launch it out, all of a sudden our result and our what we saw was different. So one way that we found that out, Rose, is, we just started to see, you know, we do track reports. We report on like what we do and all that kind of things. And then I started to see there's a little bit of a a lean toward a class of, say, gender based on what we did. And I went back to the model and take a look at it, and the model didn't have any bias there. It's the result, the model stack rank, just normal and everything else. So, you know, where then did that bias happen when actually the report come back that way? And it was really how we aggregated the data, and we point out, and we, you know, if you're gonna say send a marketing campaign, a letter, or you know, some kind of text message or whatever via phone, who's the best person to contact, right? So again, optimization. How do we get to the person that would get the message around? And one way that the system kind of, you know, not very conscious about was, hey, we just send that to the head of the household. And usually somehow the head of the household was identified as male. And that's because of a very simple fact that when we open an account, or when somebody come in to open an account, or via on the phone or whatnot, the man was the one to first provide the ID. Therefore, the tracking system said first person, second person, right? First person, give us the ID, second person, give us another ID. They are equal in our system, but to dedupe, you need to only pull out one person. And then all of a sudden, within that process, we found out, oh, we leaning towards male versus female. So that's one way that you could figure out. You kind of have to track back and look, and also use your gut to figure out how did that happen. So that was one thing that we found out, and we went back to the system and kind of fix it, right? So we basically switch and balance that out by substituting and creating other processes to make sure we insert the second person in our system going forward also.
Excellent example. Thank you.
Probably time for one more. We're kind of backing up against lunch. I want to be mindful of everybody's time here, but we could probably take one more question for breaking if there is one. Otherwise, yeah, thank you, Soumitri and Tina, for an engaging conversation. Once again, very insightful analysis into the current state of the science and where and what we can do to mitigate some of the biases that creep in either by data or by algorithm or by both. So thanks once again. And yeah, we're going to be reconvening after lunch here to listen to Woody's presentation. So hopefully you can stick around for that, and the workshop, which will be a live mob programming session. Invite y'all back for that too. So
Thank you.
Thank you.
Very well put. Thank you.